Great. Thank you, everyone, for bearing with me for that. I'm really pleased to introduce our next speaker, Terry Wallace, who's extremely accomplished, very renowned, not only in mineral collecting and mineralogy, but also in the earth sciences in general, which is actually how I first came across Terry's name. He is a renowned seismologist. He has a PhD in seismology. He was a professor at U of A in seismology for a while, and that's reading his work is how I first came across Terry's name, and then only later realized that he's actually a really big deal in mineralogy too, which is super awesome. So as I said, Terry's a PhD seismologist, was a professor at U of A for a while, but in the early 2000s, he went over to Los Alamos National Labs, where he eventually ended up as the director. He's now the emeritus director at Los Alamos. Has an incredible career on the academic side of the earth sciences, but in mineralogy as well. I think we all know him for writing, many books, many articles. He's been awarded the Carnegie Mineralogical Medal. It was awarded in 2003. An incredible career both in the earth sciences in general and mineralogy. And today he's going to take us into the world of fakes and frauds by asking, is this odd specimen too good to be true? To you. Let me get this out of here.
And I can just advance normal.
Yeah.
Okay. So good morning. And when somebody asks me about mineral oddities, inevitably it's because somebody's told me that one looks odd. And I'm not really telling you anything new here, but whenever something looks odd, there's a sort of a sixth sense that goes in with serious collectors. Is this one real? How would we tell it's real? And so on. And actually, it's pretty amazing from a science perspective how much our ability to measure things has changed so significantly in the last 25 years. I mean, you're able to do mass spec isotope ratios of 1 part in a trillion now. You're able to look and actually do a chemical structure on a crystalline material that's available only in a fraction of a microgram. You're able to do scanning point by point Raman spectroscopy now. And so instead of relying on our gut feeling, we're now verging on an age in which we're able to apply true analytic techniques to maybe help answer that. Although everything's weird, just like we saw with the emeralds, sometimes geologic conditions and nature can fool. I'd like to talk about some specific things, though, because often we're really pressed as mineral collectors or mineralogists or science in general is when something is just looks like one of a kind. And we should remember one of a kind things often are actually real and not necessarily fake, but there are ways to look at that. And so I just want to talk about that on 2 topics that are really big because lots of money's involved. And they have to do with fake silvers. We've learned a lot about fake silver wires now, and potential for fake golds. And gold has always been a controversial subject. We know individual gold specialists that have made millions of dollars on the basis of testimony and legal trials on whether it came from mine X or mine B. And so understanding these kinds of things is a worthwhile look at an oddity. The down.
Yeah.
Oh, there it is.
Yeah, it's up and down.
Okay. Yeah. And so, when we start to use the word fake, and you ask when is the first fake mineral, you actually have to go back to Neolithic times. So at Aleppo, which we now know, everybody knows where Aleppo is because of the conflict in Syria, there's a famous archaeological site in which they produced beads about 6,000 years ago. And their main thing was importing turquoise and making turquoise beads, very small ones. But when the archaeological site investigated and looked with time, they stopped using turquoise and they started producing their own turquoise looking beads by taking tusk, so the apatite associated with the tusk, and somehow heating with an iron material. We're not quite sure what it is. And it makes for a blue colored material that looks very much like turquoise, and they continue that trade. So whether they're fake or not, I don't know. I doubt that they said tusk instead of turquoise, but it's a common a common human tendency to be able to modify something for some gain associated with that. The first time that you really see an article talking about how frequent fakes are was in 1900, and this is from a quote from a curator. And curators, they're always on the lookout for fakes, but they kind of like owning them too. And the quote is, all collections contain some more or less fake specimens. Crystals on a locality stuck on a matrix from another, a fine geode, quartz geode with one amethyst crystal cemented in just right, an artificial crystal put in an artificial or in a natural rock cavity, and so on. And in fact, every year at Tucson, at least, I think every show, but Tucson is always an exciting, heavy gravity center for attracting new fakes. And a couple of these, of course, are the so-called blue hemimorphites from Mapamee. The picture is one over on the far side. And then this last year was these incredible bolyites that were stuck on matrix, a vibrant green matrix. And to assure the validity of these, both, both of these supposed finds were fortified with YouTube videos with the collectors actually getting them in place. And so, for example, the blue hemimorphites, there was probably 50 YouTube videos with these miners trucking through the lowest levels of Mapamee in puddles and then pulling out these wonderful specimens. And although not quite as dramatic, the same thing is true for the bolyites. Of course, it turned out that the blue hemimorphites were fake. Took a little while to do this, but turned out trivial once you do a Raman spectroscopy and you look at what the reflection is. And the bolyites, they turned out that they just found a really good glue that didn't simply dissolve in acetone. Okay, and it took a little while to find that, but a simple X-ray showed they were glue. And so this is an example of potential large money things which give you in terms of what you expect with fakes. So I want to go to two specifics then, but I'll give you a little bit more talking about the analytes. The first was these incredible gold cubes. Each one of these cubes, there's two different ones there, are about a little less than 2 centimeters. So they're huge. And they have limonite things attached to them one way or another, also cubic. And you see a striation pattern there. And these appeared in 2013 at the Munich show. And it happened to be one of the few Munich shows I get to go to. And so when we saw these things, it was just amazing. It's like the first thing you think is, this has got, well, there's two reasons, but we'll go to it. This has got to be fake. How could these things be real? And the second thing that was really interesting about that was it gave the location as the Lina River. Okay, that's a good kind of location because there's a bunch of mines around in that area. But when you say Lina River, you could be just saying Mississippi River. It's the largest, longest river in Russia. And it's one of 3 Russian rivers that drain into the Arctic, right? It goes from Lake Baikal to the Lina Peninsula. And indeed, there's lots of gold mining along in it, this particular river course. But there are many different gold regions within it. When questioned, there's always, well, these came out in the 60s and they've been hidden away. Very common thing to hide away the really good stuff, just wait for it to accrue more value. But again, the skepticism was quite high. When I first saw them, like I said, I am certain that these are fake. I got an opportunity now to work on these, and I'll show you something about them in a little bit here, and other specimens that came out at the same time. They showed up at the Tucson show in 2016 and 2017. And again, almost none of them sold. First of all, the prices were really high, but nobody believed them. And so the oddity here was, are they real? So, the way I view minerals is that they are telling you something about evolution within our planet. And so you've seen that from a number of talks here. Special geologic conditions what a spectacular thing. And I view the minerals, the 5,600, 5,700 minerals really are a signature of our DNA of our planet. Each one of them contains something significant about the evolution of our planet. Every other planet in our solar system is boring. Okay, and so why people want to go to Mars when they probably have 120 minerals, maybe 130 minerals if you count jarosites. But I mean, it's we have this extraordinary plethora, and many of them didn't occur at the beginning. They with the planet that's evolved, and this is a picture basically which shows the evolution of the number of minerals with time. That's from the various groups that have been working on this in terms of thinking about minerals as an evolutionary process. And we have something that, like, I'm going to talk a little bit about. The most famous mineral specimen, as far as I'm concerned, is this slice of a Canyon Diablo meteorite. Okay, and the holes you see drilled there were drilled by Claire Patterson to remove tiny inclusions of a couple other minerals from that. And this was used to date the age of Earth. And 1956, the year I was born. I don't know if there's a correlation to that, but and so I view that that's when you hold that artifact, it's like holding the Rosetta Stone. But it was the first mineral, if you will, in which modern technology was used to do something about the evolution of the planet. And so looking at these small inclusions and coming up with an age of the planet is what we want to talk about now. And then you can have minerals, for example, there's a huge number of minerals which are only formed after you have a mine. They may not be something in which you think natural, but they are natural. It's just the mining conditions. And so, the mineral at the bottom is, as a mineral, is only known from one place in Arizona. And so you could say its formation was less than 100 years ago. And so you're looking at this as you come across as, again, this DNA signature. So let me just talk a little bit about what we mean when we talk about looking at the analytic analysis. This, of course, is Canyon Diablo. This is my particular piece of Canyon Diablo meteorite. The slice there, you see a black dot in the middle. That happens to be, instead of being just iron, it's an iron sulfide. I'll show you what it is in a moment. And that's exactly what Claire Patterson was drilling out. So Claire Patterson set up a laboratory, and he was really interested in lead. He's a remarkable hero to humanity because he struggled to find ways with the mass spec to truly understand lead, saw all this lead in the background, realized we as humans were producing huge amounts of lead, largely from gasoline. And he began a 35-year crusade to remove lead from human-made sources, from everything from paint to gasoline, which made a remarkable and very demonstrated a very significant difference in the lead level of children in this country. He's responsible for reducing that lead level by a factor of 10 because of his work. Just like those that crusade against cigarettes and other things, he was taken on very much by industry, and he alone was the one that fought this battle largely this long period of time. If he hadn't been at Caltech, I happened to meet him when I was a graduate student there, really weird guy, but I mean, he's nevertheless, unlike anybody else from Caltech, but he chose to do that. But his most famous contribution, as far as you or I were concerned, he's the first one to give an age of the Earth that was very, very accurate. And he did this by being able to beat down the background levels. So from this, he looked at basically the uranium decay series. And of course, the uranium decay series, whether you go 238 or 235, you come down and you generate different isotopes of lead. So if you can isolate some lead, and you can actually assign an atomic number to it, 204 or 206, maybe 208, you can say something about what that decay sequence looked like. And he reasoned that the meteorite represented a primordial piece of material being put together when all the other planets were and was able to look at what that age must have been by looking at the ratios of the various isotopic leads that were there. And so the three minerals that he basically was able to drill out of that particular specimen that you saw was triolite, cohenite, and schreibersite. And what I really showed you was triolite, was that big black thing that I showed you in mine. And from this, he was able to calculate an age. And his age in the end that he produced was 4.54 billion years for the age of the Earth. Many people have got an age of the Earth since his time. Nobody has been able to improve that by more than 1%. And nobody at his time could do that. And nobody could do that for the next 10 years. And so thinking about what is in that meteorite, or I call it a mineral specimen, what you can get out of that to actually signify some other material is how I think about how do we determine whether something's fake or real. And one of the most significant parts for me, I'm a silver collector, is the question of silver wires. And silver wires have been around forever, right? And they're one of the most interesting to collect. On this one side over here, the first one that you see, it's on your left-hand side. That's a particular acanthite, and you see these long silver wires come out. It's about 2.5 centimeters tall. And on the other is a Kongsberg piece, and the Kongsberg piece of wires, that whole specimen is about 5 centimeters across, but there's acanthite and then the silver wire. And in the middle is a picture that was first published in 1896, which shows an acanthite matrix and looking at a reaction to grow those silver wires, seeing a release of sulfates with oxygen around there and pure silver. And it turns out that we've known this reaction forever. We just didn't really put it in context. In 1574, Ecker wrote a publication, which was kind of, how smelting worked. And what he wrote, and this is a translation as good as we can get for the translation. So if it's actually from Latin, which the thing is written in, Latin translation to English rarely works really well. But it says, lightly cut or scratch them, meaning these ores, which turned out to be acanthite, with a knife and hold them over a charcoal fire until they get hot. Then you're going to basically see wires growing out. And he says, it's fascinating. It's really cool. Everybody should do this. Okay. So what we knew right there was the first documentation of a man-made example of growing silver wires out of acanthite. So the next thing that really comes from this that's really important is Michael Faraday. So everybody knows about Faraday in terms of electricity and ions and everything else. In 1831, he was trying to figure out how to conduct electricity. And he came upon the idea of what we call solid ion conductors. So lots of people have understood if you dissolve salt in water, you can make it conduct a little electricity. But solid ones were a little bit different. And he found two solid ion conductors. Acanthite, when he heated up, he could produce an electric current, and a lead halogen, and the same kind of thing. But he wrote about acanthite, and he came up with two words that every one of us use today, and that's cation, and anion. He invented those for acanthite. Now remember, this is a guy that had no idea what an atom looked like. There were no electrons in 1831. That took, a couple English guys at Cambridge to really come up with that 100 years later. So it was a remarkable accomplishment to do that. But describing a change in temperature in acanthite and changing the ability to do conductivity is where the words ion and cation came from. Well, it turned out that everybody saw these silver wires coming around in middle, about 1990. And we basically took the 1874 recipe, and a number of people did this, found out, take acanthite, heat it up, and you get silver wires. And the specimen on the left-hand side was the Moroccan silver. Everybody saw these beautiful Moroccan silvers that were coming out, but they weren't particularly sophisticated fakes, because if you turn them over, almost all of them had blowtorch marks. But it set the stage to understand that here we have a natural material, and you can produce something that looks like it through a man-made process. And of course, part of this is that silver is the most interesting element, except for plutonium, but that's a different story. The most interesting element in the periodic table. And it has, the way I describe it to most people without going into too much detail, being that it has an electron out in the d orbit that doesn't do much, it's very promiscuous. Okay, it's willing to give up that electron just for a hug. Okay. And so when it does that, it's easy to migrate those electrons through a structure. But the structure, if you have a paramorph, not a pseudomorph, but a paramorph, and you look at these as it comes through, is changes. And of course, all silver sulfides are paramorphs. If you change the temperature of any sulfur sulfide, it will reorganize at some point. And for a canthite, of course, you're going to go from a monoclinic to a cubic structure. And when you change that structure, you provide more room for the electrons to be able to transfer that charge. So here's a picture of a monoclinic at 170, and that's for you guys on the right-hand side, no, on the left-hand side. And basically, that's a nice, what we call primary canthite. Okay, and it's about 2 or 3 centimeters tall. And so if you look in the middle there, you can see it's monoclinic structure, but when we heat that sucker up, then we can get rearrangement, and the silver ion can sit a lot of places relative to the sulfur ions, therefore promoting its transfer of an electron. And you end up with a cubic structure. And the cubic structure there on the right-hand side, it's a very nice cubic pseudomorph, maybe, now I'll call it here, what we're looking at is the high temperature form frozen in, even though it's a low temperature form from Guanajuato. But what is going on then when you change that structure? When you change that structure, as I said, you can get some conducting. Now, I said any sulfide can. The sulfide that you see there with the silver wires is from Coquichaca, and you can see the pictures on the bottom of that of some sulfide. That sulfide is actually basically Canfieldite. And so you're going to heat up the Canfieldite, or no, or jaredite, sorry, or jaredite. When we heat that up, you can still produce the silver wires coming out of that. So what happens? In the top picture here, we're going to just show you our canthite structure. And this is very notional. This comes from a John Rakovin photograph. But as we begin to heat that up, you're changing, going from the monoclinic to the cubic structure. And so you're changing density because it's less dense. And that's giving you more room to move the electrons. And when you do that, then the silver can come out. And so you can grow this silver wire out. So you're looking at any specimen that you see, you're actually looking like a silver wire. If it's attached to a canthite, you'll see the acanthite, you'll see the high temperature form, and then you'll see the silver come out. And this ionic conduction, maybe even superconduction. So it's very popular material right now for looking at films to next generation kind of chips. And the wires this mechanism became really significant in the discussion of what we call the Great Freiberg Silver Discovery in 1993. So in 1993, in all the shows, suddenly there were these huge silver wires. The silver that you see over here on the left-hand side, that's 9.5 inches tall. They're good wires from Freiberg that are documented going back many hundred years, but these were the best. And when quizzed, and I won't name names on this, when quizzed, these were all stashed away so that they could someday get them after the Stasi and the East Germans kept them from being able to put them out. And so When you pick one up, it looked kind of funny. They sometimes have a crust on the bottom of a canthite type material, but it's a crust. It's not a crystal of a canthite. It's dusty. There's bubbles in this. And it just didn't seem right. The gut feeling told you that maybe these were fake. And there were lots of stories about this, but how do you prove that's fake? So we struggled with this for a long time. But of course, modern instrumentation came to the rescue. These are real ones. So there's an Altai specimen. There's a wonderful long wire from Charnesio in the middle, and there's a big Freiberg wire from there. So we began to try to look at what is it about these wires. And so the first thing you would ask is, maybe there's something in their trace isotopes. It turns out we can't really say that's very true. It turns out trace isotopes aren't great for very much because they just vary too much across even individual geologic provinces. But we realized that silver itself contains the key. So silver, natural silver, has two isotopes, and relative abundance is almost exactly 50-50, 107 and 109. But the 107 is a little lighter, of course, than the 109. So we begin to look at the volatility associated with that. If you heat material up, even if it's solid, it still has some volatility. You're just basically exciting the silver ions, and the lighter ones are going to leave. So it turns out that if in open air, meaning low pressure, you heat up silver, it loses 107 versus 109. So that ratio changes. And so it's a fairly interesting thing to look at that. If you take that same silver and you heat it up in a pressurized system, put it in a capsule and put fluid in that, there's no volatility. 107 and 109 stay exactly the same. So if you look at acanthite globally, this is again, John Rakovac figure. We have a much bigger figure than this now. And you look at the ratios of 107 to 109, so the deltas, for those economic geologists think that you can discover everything on the basis of these ratios. You can see something really interesting here. So acanthite, silver and native gold, silver coins even smelted. In terms of, you look at this, what you see is a ratio that's basically the same as nature. So the zero line that you see along the left-hand side. Until you go to wires that you produce in open air. And then the volatility causes a significant shift. And you see a depletion of 107. And we can't produce this in any way except under low pressure systems. So let's go test all the silver wires we want. This is actually a pretty easy thing to do nowadays. It wasn't so easy when 107, 109 was a little bit hard to do on the mass spec. But now when I say it's easy, I mean, I have people. Okay. And I mean, it's a trivial thing to do. And so we've done this for almost 20,000 specimens. And to no surprise, there's a big group of Moroccan silvers, which are obviously grown in open air. There's a significant group of Chinese silvers that are grown in open air. And every silver that was associated with the great Freiberg find was grown in open air. Doesn't mean somebody directly did those. They may have got it out of an open smelter. Who knows? I mean, we've seen wonderful things. Once you take down your smelters, you get huge tellurium crystals right from Pueblo. I mean, those kinds of things happen, but it's clear that those are different. The other Freiberg silvers, so we tested many in the Freiberg Museum that are provinced with particular time, all have the normal ratio. These only the exceptional ones. In this case, I will tell you, we think these are too good to be true. So the oddity here was, indeed, they were too good to be true. So the one here you see is a Freiberg silver, the first one I showed you. I said it's about 9.5 inches tall. I don't know what that means it's worth. That's not the point I'm trying to make here. Yeah, it's different. And the other one, of course, is a really nice silver looking there. That one came from China this year. I thought it was real for sure. It's not. Well, no, it's not. It was, the wires were grown at low pressures. Okay. So let's move on to those wonderful golds that came out. And as I said, here's the Lina River. You can just see it in that map coming off the region around Lake McCall and passing through what is known as the Bodeabo Gold District. So along here, there's several gold districts, but we've decided this is the main. Okay, this is a really big gold district. It was discovered maybe 1840, maybe a little earlier. And since that time, it's produced more than 1,500 metric tons of gold. And about 95% of it is alluvial. I show you a picture up here of mining operations, and the last one I could find. It's pretty hard to get good pictures of things going on in Russia right now. But this particular one is from about 6 years ago. And at the bottom, you could see actual people digging up these large alluvial deposits along the river. And this particular photo was from 1906. And so they've been producing large amounts of gold by digging up, basically, this is like the Yukon. And so it's basically a large-scale alluvial deposit. When we say Bodeabo, we are also talking about really important moments in Russian history. So in 1906, somewhere around 30,000 people lived in this district. But they were basically, at most, serfs for a bunch of companies that were all owned by ministers to the Tsar. And so in this turbulent time, they had a huge strike in 1912. And the Tsar allowed troops to come in, and they killed 250 of the strikers. And that started the wave of strikes all the way across Russia, culminating in the Bolshevik Revolution. But we could see that we must have had a lot of gold there. Not many specimens are necessarily in historic museums. So you look in the Fersman, in the catalog, there's a bunch of things, but if you've dealt with the Fersman catalog, you'll know that sometimes the numbers change and sometimes the specimens disappear. So it's a little hard to know what was necessarily there. So are they too good to be true? There are two different types of these spectacular specimens that are listed as Lina River. There are the cubes, and the cubes with the limonite associated with them. And then there's these wonderful octahedrons. And the octahedrons are quite often on a quartz matrix. The deposit itself, it's coming, the gold is coming from, is a black shale, large-scale black shale deposit with high-temperature quartz stringers that carry the gold. So most of the gold that's being produced today in the placer part of this are very, very small particles, but they do find some really big nuggets. But these are the two things. Now, if you look at these two things and you got these two groupings, you already know something's wrong. Because first of all, who's ever seen an octahedron look like this over and over? Okay. And why do some of them cubes and why are some of them octahedrons? I mean, the key to understanding the conditions of those two things, Lonnie is going to tell you something about this. So I told you there's a lot of large nuggets. It turns out many of the large nuggets actually show you an outline of the octahedrons. So, but dealing with some of my German colleagues, they are able to track about a dozen nuggets that show these. Nobody will ever say who owns them or anything else, but there's about a dozen of these, and you can see this one. You can see the hand size. There's some giant nuggets. They have names like giant Bodeabo or baby Bodeabo, but they're many kilograms. Almost all these large ones show something that looks like an outline of a previous octahedron. There's no evidence of seeing anything that looks cubic, but maybe that's what you might expect for something that gets tumbled. I don't know. But this, you do see this. So one piece of evidence says, well, maybe, I mean, nobody's going to fake this to make those other ones real. Maybe, maybe not. So let's talk about the gold octahedrons. What do you do when you have a gold octahedron? What would make it real? We'd really like to know what the crystal structure is. It's really hard to do crystal structures for gold. Two reasons. First of all, they're very high density, high Z material. X-rays kind of suck at that, right? And the problem is that gold is easily twinned when it's under any pressure. So if you take a gold crystal and you tumble it in a tumbler for 10 minutes, it will give you an apparent non-single crystal structure. And so this is really important that the twinning blocks the way you do this X-ray. But we have a way to do this. We can use something better. We can use neutrons. And so this particular gold specimen was provided by some of my German colleagues. We did an experiment at the neutron facility near CERN. It's a single crystal. That's stunning. It's really hard to make single crystal gold, big gold crystals, and as octahedrons, but it's a single crystal. So everything we've looked at that we've actually done the structure on for octahedrons, they're all single crystals. Miniaturized quartz matrix. So what do? So then we use X-rays and we look at the contact points. Can we see a fake kind of conflict, flat, where you push something in? But more importantly, under high power X-rays, we can see twinning, pressure twinning, if it's pressed into something. It's really pretty easy to do now. None of these have any evidence of a pressure contact. The octahedron pattern is seen in dozens of gold, and now here's the real killer. So a few years ago, when I was trying to understand the Brazilian golds that were all coming out, I ran across people who were working on gold artifacts for archaeology. And gold is a really, all high Z materials are interesting, but gold is a really interesting one, is that it always contains a little uranium. And so that uranium decay will produce helium. It has a dense enough matrix structure that it will contain the helium. So it gives you a point in time when that crystal formed. So if you look at the ratio of the helium to the remaining uranium that's in that, you can get an age for this. If it's for the fake gold artifacts, are always 0. Okay, and it's used quite frequently. It's very rarely so far. The helium uranium age for these octahedrons that we've looked at, we haven't looked at all of them, right? I mean, there's 430 million years. So we have a really unusual crystal that nobody wants to believe the way it looks, but it's a single crystal. It's not pressure contacted to the matrix. And here it is, 430 million years from when that crystal was formed. Now let's keep going. Let's talk about the cubes. This is the cube I worked the most on. And the reason is, it's got to be fake when I look at it. You have these wonderful gold cluster cubes, and then it's attached to a cluster of limonite. And so, you know, if you're going to, we'll talk about the appeal of what may be a paragenesis of this. That's just really bizarre. You know, there's just one or the other. If you look at these and we do the neutron scattering, they're not single crystals. No single crystals in that. Secondly, many are attached to quartz matrix, but when we look at that, there's no evidence of mechanical or chemical enhancement. In other words, I can't see any glue, but the twinning kind of thing doesn't make any sense because it's already not a single crystal. So I don't know what that tells. I sliced through the cubes open. All of them contain patches of iron oxide, and they all have some open cavities. So we think they're probably, in appreciation for Aaron, they're pseudomorphs. But what does that mean? You know, it's really hard to mobilize gold. I mean, you have to have a lot of chlorine around or something to do that. And so there are striations on the gold, and so suggesting that looks like pyrite. It's a black shale deposit, so there is pyrite in parts of this deposited, and most of those have striations. Is it possible to come up with a scenario in which you take a pyrite, then you go to a limonite or some iron oxide, and then you find a condition you can go for that iron oxide to gold? All the golds with the cavities and everything else have low density, but every one you cut open looks like something that's been filled with grains of gold. So what do we do? So like I said, many of the specimens are attached or penetrated cubes of this iron oxide. I didn't want to say what it was because it is kind of funny material. We do get some helium in this. So it's not been, and I don't know if we should or not. I can't answer that question. It's a pseudomorph. So when you take gold out of a solution and you put it somewhere else, how do you trap the helium? I don't know. I don't have a model for that. but you get a non-zero age for it. So there is some helium there. And so the possible explanation is that maybe these are a replacement. I don't know how to do that, but I shouldn't be limited by my own imagination for the model. And so maybe it's a pyrite, limonite, gold replacement. So how do we have a methodology to give us some quantitative analysis? We got to start out and ask, what are the characteristics and measurables? So we can always measure crystal structure. We can always look at crystal chemistry, and we can do some crystal thermodynamics. So I can tell you the conditions that I can use to mobilize gold. Are they reasonable? And then we have to assign the priorities, you know, how strongly do we believe something in terms of measurable? So what's an acceptable data range and measurement error? And then we use a Bayesian model, which I won't go into because that would kill everybody in this room, to be able to add all the data together to give us an analytic level of confidence on what the material is. Oops. So let's do the octahedrons. So a p-value is a measure of how likely a hypothesis is real. And so if your p-value is 1 and you had nothing else, it means you're 100% confident that your hypothesis is correct. So when we look for gold octahedrons, we have a p-value of 0.9 for single crystal structure. The way we reason this is as 0.9 rather than 1 is that when we do a neutron scattering diagram, there's still some modest level of interpretation of whether we're doing it right, because we still have a rind of material that scatters the neutrons in a different way. We ask for the helium content. We have a higher confidence in that. So we look at all the specimens, we do the helium content, and we assign a 0.95 if you have a significant age. And we have a 0.75 for similarity to nuggets. We made that number up, I think. But we can use the Bayesian model, and we can assign a high confidence that the octahedrons are real. And they're the best in the world, right? It's still stunning if you believe me from what I said today, because nowhere else do you see octahedrons that look like this. You see octahedrons, you see Hoppered octahedrons, but these repeat over and over and over. We don't see anything else like that in the world. The gold cubes. Well, we have about a 0.5, a 7.5 for consistency in chemistry. So we looked at the chemistry, and there's always some things in there. There's a lot of copper in these, but it's fairly consistent, but we don't see it in everything. So we use just the standard deviation model to come up with 0.75. And for the consistency in the geometry, everyone we slice open, they show the same characteristics. We assign a 0.75 because we don't know what that means. We see it, but we don't know what it means. We assign 0.6 for the helium content because we have no explanation why you'd have any helium in this. 0.25 for no known cubic. There's no other evidence that anybody finds a cubic thing in the alluvial deposits, and 0.65 for an incomplete thermodynamic model. I mean, we can write the conditions, but we have not produced it in a laboratory. So what we do is we assign what we call a high but moderate confidence that they're created in nature. Now, I come from the intelligence side of geophysics. When I say something is a moderate confidence, it sounds to a mineralogist, that's a really good thing. For us, it's not that good. Okay, but I mean, in the intelligence business, but this is giving you an idea of what we think about these. So when we end this, we could tell you, we have too many questions still left to be able to answer this completely. How do you have cubes and octahedrons, one a single crystal, one a pseudomorphs, that have nominally the same locality? That really adds a flavor of uncertainty. So I don't think you can do it, but that means that there are many, many gold deposits along the Lina River. And so they may be from different places. The second one is this: we really need to continue to find a model to prove that you could do this. The skepticism that you can replace something ultimately as pyrite with gold under normal EH, pH changing conditions is high. And again, if you didn't have the intermediate step of going to limonite first, you couldn't do it, as far as I know. So we're left with this oddities discussion that's in the end that says, how good are these too good to be true? I am now confident that if you buy an octahedron, you're making a good investment. I'm not going to tell you whether to buy a cube or not. So I want to appreciate, again, the opportunity to talk about where we're going on these kinds of things. It's a very interesting activity. I never thought I would be working specifically on the golds, but the golds are something that I care now a lot about, because gold, being this heavy element, has, you know, cosmology implications. It can only be made in a neutron star collision. So when we look at the gold being collected in our planet, we can actually do some gold isotope ratios to try to understand where this neutron star collision was in proximity to our planet. And so it's my new favorite element. Well, thank you very much.
Thank you, Terry. That's super interesting. I know I have a lot of questions, but we'll open it up to the audience first. Any questions? Anne has a question.
Before we go too much into the gold discussion, I have a question back on the silvers.
Mhm.
So on the silver isotope diagram, there was a lower line there of like synthetic wire silver at lower temperatures. And I was just curious if that was like a new method people are trying to make better fakes. Yeah.
So we can, yes. And so some people have actually tried to, can you just cook the silver long enough? Because it's again, I mean, you have a promiscuous electron, so if you give it any encouragement, it'll eventually grow a silver wire. And so when you look at that there, if you do it at low enough temperatures, the silver wires so far that have been produced have all been very, very small, even after, you know, months of growth, but they don't show this strong volatility separation.
Interesting. And I guess follow up on that is how long does it usually take the higher temperature ones to grow? Or is that like in a matter of,
So,
yeah.
yeah, that's a really great question. So industry is really interested in this right now. And so I can tell you that the length of time to grow a long wire, not the wide wire is going to be a different question, but you can grow a meter long wire in a day.
Wow. Wow. Cool. Thank you.
That's super cool. So just in terms of this slide, again, it seems like the low temperature stuff, it would in principle fool you just looking at the isotopes, but they're growing little things. So you're not going to produce these magnificent specimens people are trying to sell to. So, yeah. Caleb.
The balls, yeah. Well,
my question would be, how would you approach that? A similar approach here where look at isotopes as well as some textures like that.
so I look at those because, as you know, there are similar blister balls, but not nearly as perfect, from Cornwall. And so as a favor, we looked at textures because I didn't know what else to do on this. And so what I will tell you is that textures of the Chinese ones are different. That doesn't mean they're fake, but they are different than what we see at Cornwall. Significantly different.
Cool. Ed?
Says that there is supposed to be a clay competition. And so I've been saying, Marcus, you say you come back with these things. Let's grind one up. Clay is easy to see in XRD. We do it all the time. Do you know anybody that's actually done that?
So again, I think that there's enough money invested in this. There are a number of people that are trying some things, but you know, you don't even need to grind it up, right? Even if there's a clay content, you should be able to do an EDS by space and be able to see that. I can go do that. I have not done that.
I think Bruce had a question. I'm going to come to Bruce, and then I'll get you, Dan. So.
Gold isotopes?
So you could. There are things you could do with gold isotopes. The problem what I have right now is I don't have a paradigm for the paragenesis of a replacement, and I'm not sure what the isotopes would do yet. So we do need to do something in the laboratory. At Los Alamos, we know a lot about gold. And the reason is the high Z number is kind of like the high Z number of some other materials. And so often when we shock materials and trying to understand what they would do under pressures, we have a lot of that. And I've got some people interested in thinking about that, but very little. But Gold is a really amazing material because as anybody that deals with it, the pressure twinning tells you a lot. If you take any nugget, it's a true nugget, and you do even neutron scattering, mostly it will come back as not a single crystal. But we know that many of those, especially the Yukon ones, we can just go upstream and find single crystals, go downstream from the same thing, like in Irish Gulch. They become rounded enough and they don't look like single crystals. So we haven't got a model yet to really do that. But I'm thinking about that more from a cosmology perspective than from the present crystal perspective, but there's probably something else to be done there.
Dan.
I just had a question. Are you looking at like a small crystal in the back, or are you looking at the large?
So the neutron scattering is completely undestructive, except that it irradiates your specimen for a little while. So you don't want to carry it out in your pocket. So, but it's completely non-destructive. The helium content, we have to basically destroy the material, but we can use, we use a few milligrams for a particular alkali.
Was there a question?
The difficulty with the helium then is, you'd think we'd have this in every geoscience laboratory, but helium being such a light element, you have to really have the right equipment. And so we actually outsource all the helium work to one of the archaeological firms that's doing the work. So I haven't ever done that actually myself.
I had some questions on the helium work, piggybacking on this. What is the closure temperature for helium in gold? Do you basically have to melt it to reset it?
Yes.
Yeah. And so the ages you were showing, 430 MA, is that consistent with the age of the hard rock deposits that are there?
As the 480.
Yeah. So that's,
and by rubidium dating. So
yeah. So that makes sense. That's cool. That's really cool. Were there any other questions here? The audience? If not, let's thank Terry again.